Hi, what's up guys? Today I'm going to solve a problem again about Newton's viscosity law, and I think this is a nice problem, and if you can solve it, it shows that you have understood almost all the concept of this topic. Okay, let's jump to the problem. A cylinder of diameter d. This is a cylinder of diameter d, radius of r and diameter of d, is being pulled horizontally inside a cone-shaped bearing with velocity of v using force F. This is a cone-shaped bearing. It's actually a truncated cone, and the cylinder is being pulled with velocity of v using force F. The gap between bearing and cylinder filled with a fluid of viscosity of mu. This is the gap between cylinder and the bearing all around the cylinder, filled with fluid of viscosity of mu. Okay, determine the value of F provided that velocity is constant. So we are asked to find F, force of F, when velocity is, and we don't have acceleration as a result, and we are asked to find the force. Okay, in this problem, despite previous problems, the shear stress on the surface of this cylinder is not constant along this axis. I call this axis x-axis. Okay, it's not constant along this axis. In every section, the velocity profile can be written like this. In every section. Okay, in every section, velocity profile is linear and is changing from u equals to capital V to u equals to 0 in every section. Remember, in every section, this is true. Okay, but the gap, this is the gap, I call it T, general gap, is decreasing as x increase. The gap is decreasing as x increases. Okay, I call the y direction from the surface of cylinder. Okay, so our tau is not constant over cylinder's surface. Okay, our velocity profile is not only function of y, it changes by y. When we are going from y equals to 0 to y equals to t, velocity profile changes linearly. This change is linearly. And as we go in x direction, velocity profile changes from this shape to a smaller shape, to a smaller triangle in this direction. So as a result, velocity profile is not only a function of x, it's also a function of y. X and y. Velocity profile is function of both directions. Okay, now we know that, we are aware of that, velocity profile in y direction is linear, so it should be in this form: a multiplied by y plus b, where a and or b are function of x. Okay, a or b or both of them are function of x, such that. Okay, now we need two boundary conditions to determine a and b. Note that a and b are constant with respect to y, but they are function of x. So we need two boundary conditions in y direction as usual. In y equals to 0, u equals to capital V, and in y equals to t, locally, it's local t, t in every section. Okay, u equals to 0. Okay, by this, the first boundary condition gives us b, capital P equals to capital V, and second boundary condition gives us a equals to minus capital V over t. T is the gap or thickness of fluid film. Okay, now putting all together gives us u equals v multiplied by 1 minus y over t. So where is x here? Where is x here? As we know, as we can see in the picture, t, this t, local t, initial t, and final t are functions of x. You see that t is function of x. As x increases, t decreases. Okay? And it can be observed from the figure, it's linear. The relation between x and t is linear. So we can write like this. T equals some constant called c multiplied by x plus d. This is linear relation between t and x. And also we need two boundary conditions to obtain c and d. What are those boundary conditions? Boundary conditions in x direction. Okay, what are those? The first one is when x equals 0, t equals t1. And when x equals to L, capital L, t equals to t sub 2. Okay, from the first one, we obtain that capital D equals to t1, t sub 1. And from the second one, we obtain that c, capital C, equals to t sub 2 minus t sub 1 over L. Again, putting all together gives us t as a function of x equals to t2 minus t1 over L multiplied by x, all of them multiplied by x, plus t1. Right? Okay. Now, these are mathematical manipulations to obtain velocity profile as a function of x and y, or when x and t are linearly dependent. So we can write like this. From here also, we can write u as a function of t and y equals to capital V minus 1 minus y over t. Okay, this t can be substituted from this equation. Okay, now we jump to our calculations of tau and force. Okay, for calculating tau and force, first of all, we consider a differential ring around our cylinder. This is our differential ring around our cylinder with a thickness of dx. Okay, dx. Now, what do we have when we have a free body diagram? Free body diagram for our ring. This is our ring, and we have a free body diagram for it. What do we have here? We have a tau all around this ring. All around this ring we have tau. Okay, and some forces pulling this ring. So writing force balance, sum of forces in x direction for our element, differential element, equals to 0. Why 0? Because v, velocity, is constant. Okay, so let's write the forces one by one. F minus tau dA. dA equals to 0. What is dA? dA is the area on which shear stress is imposed. Okay, from this now we have force equals to tau dA. Okay, I call this force because it is imposed on a differential element. I call this force dF, and this is dF. Okay, now writing tau, first of all, tau, as usual, equals to mu du over dy. But as u equals to u of t and y, I should write this like partial differential, like this, del u over del y. Okay, del u over del y. From this, we conclude that tau equals to mu del u by del y is minus capital V over t. As you can see, tau here, tau is function of t. It's not constant anymore. Tau equals to tau of t. Okay? Now, also, what is dA? dA equals to this perimeter of this differential element multiplied by thickness. Okay? It's equal to PD multiplied by dx. Right? Now, putting all together, df equals to minus mu v pd over t, okay, dx. This is a differential equation, but we cannot solve it yet because we have dependency to t, but differential element is dx. So we should substitute one of them as associated variable differential or associated variable itself in this equation. I mean, we should replace this dx by some relation of dt, or replace t by some relation of x. So it's better, I think, it's better to replace dx by dt. From this equation, we have dt differentiating both sides gives us dt equals to t sub 2 minus t sub 1 over L multiplied by dx. And from here, we have dx equals to L over t sub 2 minus t sub 1 multiplied by dt. Now, we can replace this dx in the equation below. Now, replacing it gives us df equals to minus mu vpd L over t sub 2 minus t sub 1, right? T sub 2 minus t sub 1 multiplied by dt over t. Now we have a simple differential equation. Solving it gives us f, integrating f from t1 to t2. F equals to mu v p dl over t sub 1 minus t sub 2 natural logarithm of t2 over t1. And this is our final answer. Okay, there's a point in this question. Note that shear stress is constant across flow direction, but it is not constant along flow direction, i.e. tau, we can write this, tau is not function of tau y, is not function of y, but tau is a function of x or t. That's it for this session, guys. And please don't hesitate to contact me through my contact information given in description part. See you.